the op-amp. Homework 3 will be combining the topic of JFET and operational amplifier. Operational amplifier, we say op-amp in short. This is our fourth topic, and until midterm you have op-amp. Before I go to the next slide, I'll talk a little bit about the basic of op-amp. The name op-amp is a short for operational amplifier. An op-amp is a very high input impedance amplifier. On the input impedance side, you have mega ohm. The range is in mega ohm. For the output impedance, the op-amp is rather low impedance, about less than 100 ohm. The op-amp has a very high gain. You will see when we talk further about the gain, op-amp can operate in open loop mode and closed loop mode, but the useful mode is closed loop. In an open loop, when the op-amp output is not connected back to the input, the gain can be 20,000. An op-amp basically is a differential amplifier which has two inputs and one output terminal. So I just mentioned it is one kind of differential amplifier. Now we will start talking about differential amplifier. The title of this slide is, I find it is misleading. It is not quite okay. It says the basic op-amp. I would like to disagree with this because this title is not talking about op-amp. It is talking about differential amp. How do I cross it out? You should read the basic differential amp. The picture in front of you is a basic differential amp, not the basic op-amp. You see there are two amplifiers, amplifier 1 and amplifier 2, which are given two names, Q1 and Q2. Q is just the operating point, and they are common emitter. The emitter is on the ground. You can apply a single bias or you can apply two DC biases. So these are pictures of two BJTs. Which terminals are connected? The emitter terminal of the two BJTs are connected. This is a PNP or NPN. What's your answer? What type of BJT?
I believe it's PNP.
It is NPN. For PNP, the arrow will be pointing inside. The emitter arrows are pointing outside of the device, so it's NPN. You can use the shortcut to remember. PNP means pointing in, NPN means not pointing in. So that's a shortcut way to remember. So see that emitters are connected. What about the input? At the base of Q1, you have a signal input Vi1, and base of Q2, you have another signal Vi2, two input signals. What about the output side? The output is taken from where? The collector terminal for each of the amplifiers. Vout1 for amplifier 1 and Vout2 for amplifier 2. So if you look at the equivalent diagram, you see this is triangle. The triangle whose top is pointing to the right. We use this symbol for general op-amp or differential amp block diagram. You have two input terminals, two output terminals. This is an extremely popular connection used mostly in IC units. There are many amplifiers, differential amplifiers, which can have two different DC voltage levels, just like this one. You have VCC, one level of bias, and on the emitter side you have VEE, another level. But it is also possible to have single or common. For example, this one is a common for the emitter terminal. Both the emitter terminal have the same VEE, but you can also put different VEE on the emitter terminal. What did I say about the op-amp? Op-amp has 2 input terminal and 1 output terminal. So this is not an op-amp. This is differential amp. Op-amp is based on differential amp. Also, when you have the basic differential amp, this is very important. There are 3 input combinations possible. So 3 modes of input. First mode, maybe I have to draw a few things. It is called the single-ended operation. What happens in a single-ended operation? On one input, you have a signal. So I can put a symbol of a signal, and the other input is grounded. This is called single-ended operation for input mode, not the output, input. You can also do the other way, doesn't really matter. You can put the input signal on the second pin. Here's the input, and this one you just, put it on the ground. The main idea is one of the input will be getting the signal and the other one will be grounded. Output can be taken from both collectors, V01 and V02. The second mode of input, both inputs, they will have some applied signal but in 2 opposite polarities. This is called the double-ended or differential input. So I put an input right here for input signal 1. The other one will be opposite polarity. This one is a double-ended input. Oh, I did not want to do that. I can also write this diagram like this. Look at this thing. I have added a signal source, and then the top one is going to the first pin, and the bottom one is going to the second pin. This is also a way of drawing the double-ended input. So you see one pin is getting the plus peak, the other pin is getting the minus peak. Then there is a third input mode. We call it the common mode input. By the way, double-ended input, you can also draw separate inputs, just like I did before. What about the common mode input? For the common mode input, both inputs, they have the same input signal and same polarity. If I draw a signal source, I think I have to draw a bit at the bottom. Let's draw the signal source. This is the signal source, signal ground, right? So this is one, and this, if you connect like this, you see both pins are getting the same signal with same polarity. This one is called the common mode input. What happens if you provide common mode input signal? Common input signals, they result in opposite signals at each collector. So they cancel out. For the common mode input, the output of a differential amplifier ideally, means theoretically, should be 0, because one pin is called the plus pin and the other one is called the minus pin, which we'll study just a little bit later. If you put the common mode input, you see as a plus, and the same peak is multiplied by minus, plus minus gets cancelled out. This does not happen with differential mode, because for the differential, one side is plus, another one is minus, so minus with minus becomes plus. Ideally, I said for the common mode input, the output should be 0. But in real life, there's a little bit of signal coming out. Now we are in the basic op-amp. Did you have any questions about the differential amplifier, the basic differential amplifier? Because we have to move on to the next, but I wanted to make sure that you understood this discussion. No questions? Can I move on?
No questions.
No questions. Now we are gonna go to slide number 3. This is the basic op-amp. Now you see what is the difference. Basic differential, 2 inputs, 2 outputs. Basic op-amp, it is based on the differential amplifier, same principle, but you have 2 input pins and 1 output side. One pin is called the inverting pin or inverting input. Usually when we do the circuit diagram in the class and solving problems, what we usually do is put the non-inverting. No, this is correct. Inverting should be on the top. Inverting input is given by a plus sign, and non-inverting minus sign. Non-inverting is given by a plus sign. What is the meaning of that? If you put a signal on the inverting input and the plus is grounded, this is a single-ended operation, right? The output will be the inverted, a mirror image of the inverting input, and then multiplied by whatever gain you have. What if you put a signal on the non-inverting and then this is grounded? So the output will be the same phase as the input. It does not flip or invert. An op-amp is a very high gain differential amplifier, high input impedance in the range of mega ohms, and the output side impedance is low, less than 100 ohms. I think I mentioned this a little while ago. It has 2 inputs and 1 output. That's the basic op-amp. So when you draw the picture for the circuit diagram, or when you are presented with the circuit diagram, this is the symbol you will see. A triangle, inside you have in plus pin and minus pin, and you have an output. When the output is not connected to the input at all, we call this open loop. In this mode, the gain is very high, maybe 20,000. If you provide 1 millivolt inside here, 1 millivolt multiplied by 20,000, output will be 20 volts. So if you put 1 volt, is it going to be 20,000 volt? No. Electronics circuits or electronics devices are not designed to handle 20,000 volt. We will see later on that why the open loop gain doesn't really matter. What matters is the closed loop gain. In the closed loop, the gain becomes much smaller. Open loop gain is higher, but it is unstable. A very important parameter and concept of this chapter is called CMRR. This is standing for common mode rejection ratio. A little bit ago, I told you about the common mode input. What happens in the common mode? Both the inverting pin and the non-inverting pin, they are getting the same signal with same polarity, which means because of plus and minus difference, the output will cancel out with each other and the common mode output should be 0. That is theoretical case, ideal case. In real life, there is a little bit of signal coming out in the common mode. So the common mode rejection ratio means it is the ability of an op-amp to cancel out or to suppress, to reject any signal that is coming out from the common mode. Why do we want to cancel any signal in the common mode? First of all, when we talk about signal, means the wave or the signal that you really want. Any unwanted signal, we call it noise. When you provide input to any amplifier, you can get your original signal, but there is also a possibility that it picks up some other noisy signal from the surrounding. When you try to amplify your signal, you want to amplify only the desired signal. You do not want to amplify the noise. So in the common mode, what goes through the amplifier is actually the noisy signal, not the good one. And a good op-amp should have a high common mode rejection ratio, which means that whatever output you get is very close to the pure input signal, and it is not a mix of input signal and some unwanted noise. A common mode, see, because the op-amp has two inputs, they are opposite in phase. If any signal that you put in common mode, they will be cancelled. And I said in common mode, the kind of signal that comes inside is noise. You want to cancel it. It doesn't get cancelled exactly completely. Most of it can be cancelled out, but not 100%. So the CMRR is an ability, a measure of the ability to cancel out the signal. It is given by this equation. 20 log of base 10, you have to take base 10 log, not the natural logarithm. In calculator, do not use ln, use the log. 20 log base 10 times AD divided by AC. What's AD? What is AC? AD is the gain in differential mode. What is the gain? Gain means output voltage divided by input voltage, or you can say output signal divided by input signal. What is AD then? Any gain that is happening in differential mode, we call it AD. It is a ratio of two voltages, same signal, so no unit. AC is the gain happening in common mode. If you take 20 log base 10 and then multiply by the ratio AD over AC, you will get a number. This number has a unit, decibels. You have to use decibels. If you do not use 20 log base 10, you just take the ratio of AD over AC, then it's just a ratio, no units. But the moment you use 20 log, you have to give the answer in decibel unit. And then V out, this is on the right hand side. The equation V out is the output equation from op amp. AD times what? This is what? V plus minus V minus. What is the meaning of that? The voltage at the non-inverting pin minus the voltage at the inverting pin. So there's a voltage difference, or delta V. This one is voltage difference in differential mode, AD times VD. This thing in the bracket, sorry, let's highlight this one. It takes everything at the same time. I hope you can see AD times this one, you can call VD, differential voltage. If I give you an op amp with one voltage, let's say you have 5 volts on the positive pin and 2 volts in the negative pin. So 5 minus 2, or minus 2 volt on the negative pin. What will you have? 5 minus minus 2. You have 7. VD equals 7. So this is AD VD plus AC, which is the gain in common mode, times this parameter. Add the voltages of the two input pins, divide by 2. This is VC, voltage in the common mode. AD/VD plus AC/VC. Any questions? We're not going to do this example yet. We'll come back to it at a future session. Are there any questions about the CMRR?
Not now.
Not now. This equation, by the way, the output voltage equation, is expressed in another way for some problems. See, this is AD/VD plus AC/VC. If you take AD/VD as a common factor outside of a bracket, you'll find AD/VD times, in the bracket you'll have 1 plus AC over AD, which is 1 over CMRR, and then you'll get VC over VD, multiplied by VC over VD. In some problems, you don't have all the information. You have the common mode rejection ratio, you have differential gain, you have some voltages, but you have one unknown parameter, which you have to find out. Later on, we'll do some examples where you can see how the CMRR problems are solved. Now the op-amp gain, let's talk about the gain. I mentioned to you in the beginning that an op-amp you can connect in a circuit in the fashion of open loop or a closed loop. Open loop means it's a configuration which has no feedback from the output side to the input side. Open loop gain typically exceeds 10,000, more than 10,000. You can have 20,000 or even more. So it's like 5 digits. For a closed loop, if you put the op amp in such a circuit configuration that there's a negative feedback from the output back to the input side, it is called a closed loop. If you provide a closed loop connection, the gain is reduced a lot. You will not have 10,000 gain. What will you have? Maybe 1, 2, 5, 10, 20, but never thousands. No. It reduces the gain, which may look to you as a loss. You're losing something. But on the other hand, a closed loop connection with an op amp, it improves many other characteristics. For example, better response at higher frequencies, the operational frequency range, which means the bandwidth of the op amp will be increased a lot, so it will be more useful. The gain will be a stable gain. There will be linear response between input and output for a large range of frequency. Always remember, as it's highlighted at the bottom of this slide, that the closed loop gain is always lower than the open loop gain. Now, look at the connection. This one is called the inverting op amp. Why do we call it the inverting op amp? Notice where the input is given and which one is grounded. The inverting pin is connected to the input V1, input voltage or signal V1. And the non-inverting pin is connected to the ground. This one is an inverting op amp. What else do you see? The output side is connected to the input side by means of a feedback resistor RF. Sometimes it is written as R2 in the circuit diagram or in some exercise problems, but this is the feedback resistor. You can actually calculate the gain. The voltage gain of this inverting op amp is negative RF over R1 times the input voltage. There's a derivation which I often ask. Here's the derivation that I would like to do in front of the screen. First of all, what did we tell about the input impedance of the op amp? Is it high or low? It's in the mega ohm range for the input impedance. So high or low?
High impedance.
High impedance. So right now I'm doing a sketch. Imagine from this source the current is coming in. We shall call it current I1 because it's flowing through resistor R1. At this node, you think that some will be split to the resistor RF. We can call the current IF, and you might think that some of it will pass through the op amp itself. Let's make it IF. You think some of the current will go here? No, it will not go like that. So because of the high input impedance, it does not pass the op amp. Your input current and input signal I1 will go all the way through, which means I1 equals IF. I put an equal sign. I1 equals IF. Also, there is another assumption we always have to make in case of an op amp. We always have to say, this is an assumption, V minus equals V plus. This is one of the assumptions that you use to derive so many equations. V plus is here, the voltage at the plus pin. We call it the V plus. And V minus is here, V minus. V minus is not V1. V minus is the voltage at the pin. So what's the equation of R1? If you use Ohm's law, this is V1, this is V minus, and R1. I1 equals what? I1 equals V1 minus, it is the difference between the 2 points, V minus divided by R1. And I said I1 equals IF, isn't it? This equals, what is IF? It's flowing from left to right. So this voltage, V minus minus V out divided by RF. Do you understand this part? It's the simple Ohm's law. And the assumption that you have to say V minus equals V plus. What is the voltage at V plus? What is the voltage at V plus?
0.
0. So V minus equals V plus, which means this is 0. V minus is 0. It gets cancelled out in the equation. We don't use it anymore. I'm going to cross it. Cross it. Left hand side equals right hand side. You see V1 over R1 equals negative VO divided by RF. So what is AV then? AV is V out divided by V1, right? If you take V out over V1, it will become minus RF over R1. So what is the output voltage equation then? V out equals minus RF over R1 times V1. This is the gain factor. If you take the value of RF same as R1, the gain is 1. But you have a minus sign. This is the same as JFET and BJT. The input and output relationship is a 180-degree phase shift. That's what it says. This will happen in the input where the input is inverting pin. This is the inverting op-amp gain. So this is the formula. Remember the derivation I asked in the exam so many times. Derive the equation for the formula of this op-amp gain. I will give you an op-amp circuit, maybe inverting or non-inverting, and I ask you to derive the output voltage formula. Derive means to do step by step. But 95% of the students, they just write the final formula. The final formula is already on the formula sheet. I know it. What I ask is you derive, so they don't get the full marks. If it's a 3-mark question, maybe you get 1. If you give the final formula only, you get 1. You will not get 3, depending on how many steps are involved. Then this is an interesting concept of virtual ground. In the topic of op-amp, we use a term called virtual ground. It is used to describe the condition where the input voltage, VI, it's not V1, remember VI is here, VI, V and then I. At the inverting input, the voltage is 0, describing a condition where the voltage is 0 at the inverting input when the non-inverting input is grounded. I'd like to give some number to illustrate this example. Let's say the op-amp is operating in open loop mode. There is no feedback loop, there's no feedback resistor. Let's say your output voltage in the open loop mode is -10. And the open loop gain, we will say, is 20,000. If the output voltage is -10 volt and the gain is 20,000, what is the input voltage? What will be the input voltage?
-2000.
No, at the inverting. Now
Oh.
we are talking about inverting, so it's a positive one.
Oh.
It's 10 divided by 20,000. What is that? This is the output. What is the input? Gain is 20,000. So input voltage, if you take 10 over 20,000, you get 0.5 millivolt, half millivolt. This is VI, half millivolt in the open loop. Let's say now you close the loop. Now the gain is 1. Now I don't worry about open loop anymore. The gain is 1, which is typical of an op-amp in closed loop. Because once you close the loop, make a feedback, the gain decreases. The output voltage is 10, still negative 10, your gain is 1. What is the input now? Input is now here, V1. What is the input? It's 10. 10. 10, because if the gain is 1, means RF and R1, they have the same value. The ratio is 1. So negative RF over R1 times V1 is minus 10 when you are in the closed loop. Compare these two values. One is 10 volts in the closed loop mode, and in the open loop, the input pin is receiving maybe half millivolt. If you compare 10 with half millivolt, what is that? 1 millivolt is 1,000 times smaller than 1 volt. Half millivolt is even half of that. Compared to the all other input and output voltages when the op-amp is running in closed loop, we can say VI. The input pin voltage is close to 0. If VI input pin voltage is 0, what does that imply? If this voltage is 0, 0 voltage is also meaning of a short circuit or ground. If you decide that compared to 10 volt, half millivolt is close to 0, it leads to a concept that there is a virtual short circuit or a virtual ground. It thinks that you are tempted to think that there's a short circuit because 0 volt and here is ground, there's a short circuit. Physically, there is no short circuit, but the concept makes you think like that. That's why it is called a virtual ground. See, where does it happen? Where R1 and RF connects, this is the pin. So between R1 and RF, if you draw the equivalent circuit, this is your input signal V1, R1 and RF. In the middle, when the input non-inverting pin is close to 0 volt and there is no current passing through. There is no current passing through. This might be counterintuitive. When you see a 0 volt, it's a short circuit, a lot of current will pass through. But we know the op-amp is high input impedance. It does not allow the current to pass from minus pin to plus pin. So the ground concept is a virtual ground. It is not a real ground. So instead of really getting short and going to the ground, whatever input current you have coming in, instead of going to the ground, it will pass through the feedback resistor. The reason is explained here again on the left-hand side. The op-amp has such high input impedance that even with a high gain, no current will go through the inverting pin. All of the input current will pass through RF. Any questions? So the main idea here is a virtual ground is not a real physical ground or real physical short circuit. It's a term to describe the condition of the inverting pin voltage when the non-inverting input is grounded. That is the meaning of virtual ground. Sometimes it is asked in some semesters, the question is asked, and then you are expected to describe. Some semesters I ask, some semesters I skip it. To the next one then. You are ready for the next slide?
Yes, sir.
So what are some of the common circuits you can make by using op-amp? First one is an inverting amplifier. We have just seen an example of an inverting. Maybe you have 1 volt, you want to make it 5 times larger, you take the ratio of RF and R1 is 5. RF has to be 5 times greater than R1. You put 1 volt, you're going to get minus 5 volts. Like 1 and minus 1, peak to peak, then you're going to get minus 5 and plus 5. You multiply your input by 5. This is an inverting amplifier. You might be guessing, what if I do not want the signal to invert? I want in the same polarity. That is also possible by using a non-inverting amplifier. Just like we have derived the equation of inverting amplifier, we can also derive the equation of a non-inverting amplifier, which we'll do next. Then there is one is called a unity follower. If you want to make the output signal exactly same as the input signal, no phase change, nothing, it is called a unity follower. After that, we have an amplifier connection known as summing amplifier. It sums means it adds. You have so many signals on the input side. Maybe you have 3 different input signals coming inside. You can add all of these signals and then amplify. We call it summing amplifier. By using resistors and capacitors as input or feedback element, you can also create an op-amp circuit which acts like an integrator. So the input is a function of something, maybe y is a function of x. You can integrate, or maybe a time varying voltage function. You can integrate and make it integral of input voltage t of dt. Similarly, you can create by using different combination of resistor and capacitor on the input side. You can make a differentiator of amp circuit. So the output will be, the equation will be dV over dt, where V is a function of time. That is also possible. We will do each of these, and one of the examples, very common examples in the class, is I give you an equation and then I ask you to design a circuit. Sometimes the opposite is done in the exam. The whole circuit is given, and then we ask you to find out what is the output at different stages of the amplifier. The second case is ideal for online exam because in paper exam you can draw the circuit and design. For the online exam, how will you draw? So we just give you the circuit and ask you to calculate the different parts. Inverting amplifier and non-inverting amplifier. Right now we are at this point. View, read more. We have seen already the inverting amplifier. V out is minus RF over R1 times V in, which is V1. We derived the equation already. For non-inverting, we have not derived the equation. How does the non-inverting pin or non-inverting connection connect? Your input is on the plus pin. Here is your input voltage. On the minus pin, it goes to the ground through R1, and then feedback resistor is connected from R1 all the way to the output voltage. As you can see, the output voltage equation is V1, input times 1 plus RF over R1. There is no minus sign. Can we derive it? We can definitely derive it. How do we derive it? What are the assumptions that you have to make? First of all, remember V plus for an op amp, V plus equals V minus. What is V plus? What do you see the voltage of V plus? It is V1. V1, correct. What is the voltage of V minus? V minus is sensing this voltage. What is the voltage? If you carefully look, what are connected? V out connected with RF connected with R1. This is a voltage divider. At this point, what is the voltage? V out times R1 divided by R1 over plus divided by R1 plus RF. So V minus on the right hand side, I will write. Do you understand where it's coming from? Voltage divider. V out R1 and over R1 plus RF. That is what is sensed by the V minus pin. So what is V out over V1 then? Or what is V out? If you rearrange the equation, V out becomes V1 cross multiplying R1 plus RF divided by R1. If you further simplify, you'll get V out equals V1. This is V1 and then 1 plus RF over R1. This is simple one, not very complicated. 1 plus RF divided by R1. That's the derivation. You can derive like this. Look at the equation. V out equals 1 plus RF over R1 multiplied by V1. This is for the non-inverting op amp. Any questions? So I showed you the derivation for both the inverting op amp and the non-inverting op amp. Do you have any questions? No questions? Can I move on?
Yes.
All right. Yes? No? Somebody saying something?
Yes, I'm saying something.
Yes. What were you saying? You have a question?
Yeah, I just came back. So I just came back from the toilet. So the one that you do it right now, it is called what now?
Non-inverting. Non-inverting amplifier.
So like on the exam, like do we need to do like that also?
Some semesters I ask you to derive, yes. These two formulas are already on the formula sheet, I believe. So when I ask to derive, the student, when they give just the formula, you don't get the full mark. Finally, you have to come to this formula, but how do you derive the formula step by step? That is the main question. It is, yes, it is asked. It is common for me to ask this kind of question for this chapter.
Just like only this chapter, right?
There are some other chapters too, maybe after the midterm.
Oh, okay.
After the midterm, we have 2 or 3 topics where you have to do calculus. Just a little bit, not too much. What is the next type of connection using the op amp? It's called unity follower. In the op amp, here you have V1, and then the output terminal is V out. The output terminal fed directly back to the input terminal. No resistors, no components, nothing at all. Again, using the assumption V plus equals V minus. What is the voltage at V plus? V1, input voltage. What is the voltage at V minus? See where it's connected, V out. So V1 equals V out. As you can see, they have exactly the same input and output. It is called a unity follower. No polarity change. If you put an inverting op amp with a feedback, you'll get change polarity. The intention is making V out same as V1. You might be asking the question, Achan, So you want a positive voltage, right? Why do we need to do this thing? You can just use a non-inverting op-amp, isn't it? But you see, for the non-inverting op-amp, what is V out? It is V1 times something else. 1 plus RF over R1. If you want to make V out exactly as V1, the ratio of RF over R1 has to equal to 0, which is impossible. It can be 1, it can be more than 1, it can be less than 1, but it cannot be 0. So that's why you have a unity follower. Then you have a summing amplifier. After summing amplifier, I will backtrack a bit. I'll backtrack and then I will show you maybe 1 or 2 examples using common mode rejection ratio, because it's very important that you understand the concept. What is the summing amplifier? It sums or adds many input signals together and provides you an amplified output. Since the op-amp has a very high input impedance, if you have multiple inputs, you can treat them as separate inputs. For example, let's focus on the first input. Only the first input, forget about V2 and V3. First input, we have an inverting input pin. So this is an inverting amplifier, and the first input path is here. What is the output? V out equals minus RF over R1 times V1, right? Minus RF over R1 multiplied by your input. Now consider the second path. If you consider the second path separately, you have another amplified signal. What is that amplified signal? You add it. You add that signal. So we're going to add everything. Add what? Minus. It is minus because it's going in the inverting pin. Minus RF over which one? Which resistor will take? For V2, R2 times V2. And then you add one more. Put a square bracket. You can add, if you plus and then add another one, it is minus RF over R3 times V3. So in the bracket, what will you have? Minus RF over R3, close the bracket, and you have to multiply by V3. Where should I put it? I ran out of space, maybe on the right hand side. V3. If you add all of this and you simplify the expression, it's like this. V out equals minus, because everything is a minus sign. In the bracket, you add the gain times the input voltage. You can have more. You can have 5, 6, 7. It doesn't matter. But this is called a summing amplifier. Any questions about this one? What is a unity gain amplifier? Sometimes I ask this as well. Unity gain means the gain is 1. If you have a unity gain amplifier, RF and R1, they have to be the same. RF, R2 have to be the same. RF, R3, they have to be the same. Means the ratio of RF to the input resistors is 1. Please take a look at this one while I go to your teams and try to find the problem for common mode rejection ratio. Give me a few moments. You can take a look, and if you have any questions, you can let me know. I'm looking at your class notebook. Op amp, common mode rejection ratio calculation. Okay, I have example 10.21 and 10.21 and 22. They're kind of near the end of the chapter, but I'm going to copy and paste. Did anyone have any question about the summing op amp?
No.
Okay, in a few moments from now, we will switch the screen to our collaboration space inside the Microsoft Teams. I just need to make a few edits before I can show you the screen. Okay, it is worked out, so I'll erase the solution first and we're gonna work together. Where's the eraser? Okay, now I will switch the screen. Screen sharing is off. You should be seeing now op amp CMRR calculation example 1. Can everyone see?
Yes, we can see
Yes,
it.
I do.
Okay. An op amp is presented to you in two cases. I think I have to, can I actually minimize the picture a bit so that we can see full screen? Okay, maybe this one is all right. This is an op amp. There are two input pins. V plus, you have input voltage half millivolt. At V minus, you have input voltage negative half millivolt. What is V out in this case? 8 volts. So again, listen and observe very carefully. Two inputs. One is half millivolt, the other one is negative half millivolt. The output voltage is given as 8 volt and it is equivalent circuit. You see it says VD, means it is operating in the differential mode. So you provided differential input, you're going to get 8 volts output. And the differential voltage is 1 millivolt. How do you calculate VD? VD is what? V plus, it is always take from the plus pin. V plus minus the negative pin voltage. This is VD. So half millivolt minus negative half millivolt. You're going to get 1 millivolt. This is VD. This is V out. This is your input. This is your output. What is the gain in the differential mode? What is AD then? What is the definition of gain? Output divided by input. What's your gain? Eight volts divided by 1 millivolt. What do you get? 8,000?
Wait, teacher.
V out is 8 volts. Differential input VD is 1 millivolt. So what is your gain? 8,000. Now in the common mode, let's see what happens. Input pin plus pin is 1 millivolt, and input pin on the minus pin volt is 1 millivolt. I told you what about the common mode? Same signal, same polarity. And in the common mode, you're gonna get 12 millivolt output. So this is the equivalent circuit. What is the common mode voltage? How do you calculate VC? VC equals what? According to that formula, VC equals V plus add V minus divided by 2, make it half. So 1 millivolt and 1 millivolt divided by 2, you're gonna get exactly 1 millivolt VC. Your output voltage when it is common mode is given 12 millivolts. So what is your common mode gain AC? What is common mode gain for AC? V out in the common mode divided by the common mode voltage VC. What's the gain? Tell me, what's the gain?
And is it 12,000?
Is it 12,000?
Just 12?
Just 12.
Just
You are
12, okay.
dividing 12 millivolt with 1 millivolt. Here you are dividing 8 volt with 1 millivolt. That's why it's 8,000. This is 12. So differential mode, you have a lot of gain. Common mode, you have only 12. That is what you want. The typical signal coming inside the common mode is a noisy signal. You don't want to amplify the noise so much. Then, what is the output voltage? What is the output voltage? Yes?
Like one more thing, when do we like convert like that, like the first one 8,000, but the second one you get only 12? Like when do we like convert it to be like the smallest number one?
What do you mean by converting?
Like how to call? Like the first one we get like the answer 8,000, right?
Yes.
So like can we like answer like from 8,000 change to like 8 only? The same like the below one?
No, you cannot change because the output in the differential mode is not same as the output in the common mode. Ideally,
okay.
you should have 0 volt output in the common mode. This is theoretically 0 volt, but the amplifier still picks up some signal in the common mode, which is noise, and then it tries to amplify a little bit. It's not the same. That's why you cannot write 8.
Okay.
And the equation, the formula for differential voltage is this, VD. Formula for common mode voltage is this. They are not the same. So you cannot just say from 8,000 I become 8. No, no way. So what is the output? What is the final output of this op amp then? We have seen the formula in early this class. AD BD plus AC BC. So you can take 8,000 times 1 millivolt plus, you can say AC BC. What is AC? 12 times 1 millivolt. 12 into 0.001 volts. What do you get? 8.012 volts. If you take AD-VD plus AC-VC, it is 8.012. From this total output voltage, 8.012 volt, how much of it is due to the differential mode and how much of it is due to the common mode? Your differential output voltage is 8 volts. and your common mode output voltage is 12 millivolts. You see, so whatever you're getting is mostly because of the pure signal. Differential mode is your desired signal, and only a little bit of it is due to the noise, the common mode. So I would say this amplifier is quite a good common mode rejection ratio, which we can calculate next. What is the formula for CMRR? Common mode rejection ratio. Let's say you just want a ratio. You take AD over AC. What will you get? $8,000 divided by 12. What is the value?
You get 666.67.
Yeah, it's like 666.67. This is a ratio, no number. But if I ask you to express in decibel, you take 20 log of this thing, 20 log of your answer. I'm going to do in the calculator 20 log of this answer. 56.48 decibels. 56.48 decibels. When you multiply the ratio with 20 log of base 10, the answer has a unit, dB, decibels. I also brought in another formula. V out is this one, AdVd plus ACVC. If you take AdVd as a common factor, you can see in the bracket you have 1 plus AC over AD times VC over VD. Because AdVd gets cancelled out. What is AC over AD? It is common mode rejection ratio's inverse. So 1 over CMRR, and then you multiply VC over VD. In this problem, CMRR is not given. But in some problem, CMRR is given, the other things are not given. So there are 3 ways of writing the same equation. Any questions about this one?
No.
Okay, and then let's see what else we have for CMRR. I think we have another problem. This one is probably worked out already. It's a worked out one, but I'll show you nonetheless. Determine the output voltage of an op-amp for input voltages of this one. First pin 150 microvolt and second pin 140 microvolt. Amplifier has a differential gain AD 4000. The value of CMRR is 2 cases, 100 and 10 power 5. So we express the equation like this. V out is AdVd times 1 plus 1 over CMRR Vc over Vd. How do I know to calculate Vd and Vc? What is Vd? Vd is V plus, the large one, V plus, subtract V minus. So if you take 150 microvolt, subtract 140, you have 10 microvolt. That is differential voltage input, 10 microvolts. It is not output, it's differential input voltage. What about the common mode voltage? V plus add V minus and divided by 2. So 150 plus 140 microvolts, it is 290 divided by 2. What do you get? 145 microvolts. That is Vc. In the case of A, when the common mode rejection ratio is 100, calculate the output voltage. We know AD 4000 multiplied by 10 microvolts and then 1 plus 1 over 100 times Vc over Vd. In the case of 1, you have output voltage of 45.8 microvolts. In the case of 2, when the CMRR is very high, you have output 40.006 millivolts. First one is 45.8 milli, second one is 40.006 millivolts. When the common mode rejection ratio is high, the output is mostly due to the differential voltage. But here you see it is 5 millivolts more because the common mode rejection ratio is quite low. How do we verify that? Multiply, okay, if you want to find the differential input voltage or differential output voltage, AD is what? Differential gain is output voltage divided by differential input. So find the output voltage in the differential mode. What is the output voltage? $4,000 times 10 microvolt. How much is it? Is it 40 millivolts? How much is
I
it?
got 40,000.
40,000? I think I put a wrong calculator. Hold on. 4,000 times 10
10.
and negative 6. 10 power negative 6.
Oh wait, micro 6.
40 millivolts. 0.04 volts is 40
Yeah.
millivolts. 40 millivolts.
40
This
millivolts.
you will get in the differential mode. Do we have? Yeah, we can find the common mode. Do you have a common mode gain? No, common mode is not given. Common mode voltage we can find out is 145 microvolts. But you see only from the differential gain, V out is 40 millivolt in the differential gain itself. So if you look at the final answer for high common mode rejection ratio, it's 40.006 millivolt, which means the output is mostly because of your desired signal. But here the output is almost 6 millivolts more. That is coming from common mode. The ratio is quite low. The rejection ratio is low. Is this 100? This is 10 power 5. If you want a good op amp that easily gets rid of the noisy signal, you should have high CMRR. Now we'll switch back to our lecture slide. We stopped at this one, but next I'll just show you integrator and differentiator quickly. I think in the next class we can start doing some examples, more examples. This is an integrator. If you have R just after the input and capacitor as a feedback element, this op amp is acting as an integrator because V out is this equation minus 1 over RC times integral of input voltage. We are assuming a time function, so output voltage is a time function. Integral will be its integral of V1 of t dt. Do not forget the minus sign. It is given in the inverting pin, so output voltage will be a 180-degree phase shift of the input voltage. What type of usefulness does this circuit have? It is used in a circuit called low pass filter. At the end of op-amp chapter, we will see frequency filters. Low pass filter means the low frequency input you will see an output. When it becomes too much high, then it will not provide you any output. So it passes the low frequencies. Similarly, you can swap the position. You can make the capacitor the first element after your input and resistor as a feedback element. If you do that, you no longer have an integrator. What you'll have is a differentiator. The output voltage, you see, it is still, the input is still on the minus pin. So the output voltage has a minus sign, minus RC dV over dt. We're assuming voltage here is a function of time. What voltage is a function of time? It's a sinusoidal voltage because it changes with time. This one is used in high pass filter circuits. Means any low frequency will not be shown on the output side, but after you pass a cutoff frequency, it is high enough for you, it will pass the high signal. For a low pass filter, it's like this. So let's say you have V out, and then let's make it V out. And then you have a frequency. It may not be a linear scale. It may be a semi-log scale because this is linear frequency, usually in log of base 10. For a low pass filter, you will keep getting outputs as long as it's low, but at some point, I'll show you the real situation. Ideally, it will cut off, but in real life, it will drop a bit, and then when it's too high, no more output. For the high pass filter, it's just the opposite. For the high pass, this is your output, or you can take in terms of gain. This is frequency. It will pass only the high frequency. So low frequency, no output, no output. At some point, the output will rise, and then when the frequency is high enough, you will get your output voltage. We'll leave it at that. In the next class, we will try to do a problem. Try to design this circuit. It's a design problem. I'll tell you what it looks like. V out equals half sine x plus 2x squared minus 4. Maybe I'll give you a different number. On the output side, how many elements are being added? 3 elements. So 3 different signals are being added. You know that this is a summing of m. And then you see sine x, x squared, and 4, and the inputs are given cosine x, and 1 volt. If you take d dx of cosine x, you will get sine x, so you know you will need 1 differentiator. If you take integral of x dx, you will get x squared over 2. Because x became x squared, for this part you will need an integrator. And then plus 1 became minus 4. So you need an op-amp with a gain of 4. You have to maybe add more stages to get the correct sign. You can think about it for the next class. Today I'll stop at this point. Did you have any questions for today? Any other questions?
Yeah, I don't have right now.
No, sir.
No questions? Let me take the attendance. Balan,
Yes, sir.
Tirawut,
Yes.
Napatra,
Yes.
Pakon,
Yes.
Rajay.
Yes, Sajed.
After Rajay, we have Jonikan,
Yes ค่ะ
Michelle,
Yes ค่ะ
Phil.
Yes, sir.
Okay. Silicon,
Yes ค่ะ
Visalut,
Yes, sir.
Yucheng,
Yes, teacher. Yes.
Sisihan,
Yes, Sajed.
Patompong,
อย่าครับ
Kungsu,
Yes, sir. Yes, teacher.
Martin,
Yes, John.
Kolawit, Kolawit, Pichayut,
yes ครับ
Jimma,
Yes, I'm here.
Sonyuan,
Yes, I'm here.
Sathawat.
Yes,
Sathawat
sir.
is here. Okay, Yapeng,
yes
Seni,
yes I'm here
Silipop,
yes อาจารย์
B2,
yes I'm here
San An,
yes
Waramet, is Waramet here? Somebody send me a message. Was it Warapat or Waramet? Navawan,
Present.
Nathapok,
yes I'm here
Warapat has to leave. He has a family emergency. Nataya,
Yes, teacher.
Pichayapon,
Yes, sir.
Komchan,
Yes, I'm here, sir.
Piladon,
yes I'm here
Titsanapong,
Yes, I'm here.
Atitya,
yes I'm here
Tasin,
Yes, I'm here.
Sukaina,
Yes, teacher.
Sirin,
yes teacher
and Mr. Min Luin U from section 555. Min Luin U is not here. Normally he doesn't come on Thursday. All right, see you next week then.
Thank you, teacher.
thank you ครับ thank you
You're welcome.